We're going to talk about note cards 48 and 49, exponential growth and decay. And the difference between the two note cards is 48 we have a formula and 42 we have a different formula that we're going to use for different situations and cases. Let's just start with note card 48. We have growth and decay can be modeled by this formula here. A of t is equal to A naught times 1 plus r to the power of t, where A naught is the initial amount, A of t is the new amount after time t occurs, t is time, and r is the rate of growth or decay. So if it's going to be increasing or growth, it will be a plus r. If it's going to be decreasing or decay, it'll be a minus r. Let's just start taking a look at some of the examples. Let's start with number 1. Okay. Number 1 says, suppose that a radioactive isotope decays so that the radioactivity present decreases by 15% per day. If 40 kilograms are present now, find the amount present A, 6 days from now, and B, 6 days ago. So let's just start with part A. First thing I want to do is I want to write down my formula. A of t is equal to A naught times 1. I'm decreasing here. It says decreasing, so I'm going to use minus r. Minus r to the power of t. So let's see if I can label what we have as I'm rereading the problem, which I always encourage you to do. Suppose that a radioactive isotope decays so that the radioactivity present decreases by 15% per day. That means R is going to be 15%, but we won't use the percent, we will use 0.15. If 40 kilograms are present now, that's A naught. The initial amount A naught is 40 kilograms. Find the amount present A 6 days from now. That tells me that T is going to be 6. So I'm looking for the new amount, A of t. So what I want to do is I want to find A of 6. A of 6 is equal to A naught, which is 40, times 1 minus R, which is 0.15, to the power of t, which is 6. Once I do this, all I'm doing is simplifying the right side of the equal sign here. This is over here is simply function notation. All I need to do is plug this into my calculator, and that will give me my answer. And so when I'm going to click my calculator so I can show you how to put this in at least one time. And when I do that, this is going to disappear. Okay, so I have 40 so I have 40 parentheses 1 minus 0.15 close parentheses to the power of 6. And that's 15.086. You always want to round up to 3 decimal places when you're working with numbers like this. The only time you do less than that is when you're working with money. When you're working with money, you'll round to nearest cent or 2 decimal places. So my answer for part A of number 1 is 15.086. Now, if I'm looking now at this next part, B, part B, my formula is going to be a little bit different. I'm going to have A of -6 because I want 6 days ago. That means I want minus 6 for time t. So the difference in part B is going to be that t is equal to negative 6. So I have a of negative 6 is equal to a naught, which is still 40, the initial amount, times 1 minus 0.15 to the power of negative 6 days ago. So I'm going to plug that into my calculator. And that's going to be 106.059. 106.059 kilograms. Okay, moving on to number 2. If Sam deposits $5,000 in a savings account that pays 8% interest compounded annually, then how much money will be in the account after 9 years? Again, write my formula down first. A of t is equal to a naught times 1 plus r in this case, because we're increasing. Okay, we're going to deposit money and it's going to pay 8% interest. That means it's going to be increasing, plus r to the power of t. So the initial amount, a naught, that's what he's going to deposit. That's 5,000. R, the rate, is 8% or 0.08, and time t, 9 years. So t is equal to 9. And I want to know how much money is going to be in the account after 9 years. That's the new amounts. That's a of t again. So I'm going to be looking for a of 9. A of 9 is equal to a naught. My initial amount is 5,000. Times 1 plus 0.08 to the power of 9. And when I put this in my calculator as I did before, you will get this answer rounded to the nearest cent, $9,995.02. Moving on to example 3. A house bought 5 years ago for $100,000 was just sold for $135,000. To the nearest tenth of a percent, what was the annual growth rate? I'm looking for the rate this time. So here in this case, I do not know R. I have to find R. Okay? So I'll start again with writing down my formula. A of t is equal to a naught. And then I have 1 plus or minus the rate, whatever we decide we need to put here, into the power of t. Okay, so what do we know about the problem? We know that the house was bought 5 years ago, so the time is going to be, t is going to be 5. The initial amount is what the house sold for initially, so a naught is going to be 100,000. And it gives me what it's worth now. That means it gives me A of t, the new amount. A of t is 135,000. So what I'm looking for here is R. Now let's think about this. And I put a plus or minus here because we need to decide on our own what kind of formula we're using here. If I bought a house for $100,000 5 years ago and today it's worth $135,000, that means that it increased. So I'm going to use a plus here. So I'm going to plug in what I know. A of t is 135,000 equals A naught is 100,000 times 1 plus r that I do not know to the power of t, which is 5. So now I'm solving for r. The way I'm going to solve this, you've seen this solved this way in Algebra 2. We haven't done a problem like this year. Pay close attention because we're going to use those skills that we developed yesterday in reviewing our exponential laws. Okay, so I have $135,000 is equal to 100,000 times 1 plus r to the power of 5. Now remember, when I'm solving an equation, I work backwards from PEMDAS, which means I'm going to do all my adding and subtracting first. Have some addition here, but it's inside these parentheses, so this part will be last. Okay, so I'm going to divide first. I'm going to divide by 100,000. This cancels. 135,000 divided by 100,000 is 1.35 equals 1 plus r to the power of 5. So if I have something being raised to the power of 5, that means that I need to take the fifth root of each side to be able to get this power of 5 to go away. Now, quick review from yesterday. You got to mind your P's and Q's. Any number to the power of P over Q is equal to the Q root of x to the power of P, or the Q root of x to the power of P that way. I want to use this information. You should be able to see right here if 1 plus r is one number, because this is all being raised to the power of 5. If I want to take the fifth root here to make that power of 5 go away, you should see, if I write it like this, that Q is 5 and P is 1. Therefore, writing 1 plus r to the fifth power, if I have 1.35 equals 1 plus r to the fifth power, and I want to take the fifth root of it, that's the same thing as saying I want to raise each side to the power of 1/5. Raise each side to the power of 1/5. Because if I have the fifth root of some number, look right here, everybody. If I have the fifth root of some number, that's the same thing as saying that I have x to the power of 1/5. Okay? Taking the fifth root, like I wanted to do initially, is the same thing as raising to the power of 1/5. Now, if I look at this using my exponential laws, if I have a power outside the parenthesis, this power has to be multiplied to the power inside. And what's 5 times 1/5? It's 1. So this gives me 1 plus r to the power of 1, or just 1 plus r. Makes it go away. Equals 1.35 to the power of 1/5. When I put 1.35 to the power of 1/5 in my calculator, I get 1.062. And I'm not going to show you that because as soon as I click the button to use my calculator, all of my work's going to go away, and I think it's I think everybody knows how to put 1.35. If you're putting it in your calculator, right here, make sure you do it like this. It would be 1.35. Then you would put the little caret symbol, and it'll open up a little box, a little text box, and you would make sure you put it in parentheses because it's a fraction, 1/5. And that will give you 1.062. Continuing to solve for r, I subtract 1 from each side. And I get that r is equal to 0.062. And since it's a rate, I'm going to move that decimal 2 places to the right. So r is equal to 6.2%. My house appreciated 6.2% over the last 5 years. And that's note card 48. Now let's talk about note card 49. Note card 49 is a little bit different, and I will go ahead and tell you that note card 49 will be used for problems such as half-life problems, or doubling problems, or tripling problems. And I'll show you what I mean by that. We have a new formula. A of t is equal to A naught, which is still the initial amount, times B. I'll show you what B is in a second. T is still time, and we have K here. K is going to be the time needed to multiply A naught times B. And instead of me trying to go into some kind of discussion to explain that to you, I think you will understand it better when I work a problem. So let's just look at number 1. Okay, first of all, I am going to rewrite my formula. A of t is equal to A naught times B to the power of t over k. Example 1 says a bank advertises that if you open a savings account, you can double your money in 12 years. Here's the key word, double. When you see things like double or triple or even half-life, which we're about to see on the next problem, that's B. So B is going to be 2 because we're doubling. Now remember, the note card tells you that K is the amount of time you need to multiply A naught times B. That means that K is going to be 12 because it takes 12 years to double. It takes 12 years to double, so K is going to be 12. How much money will you have in the account in 5 years? T is 5. Time we're going to be dealing with here is 5. If you open the account with 3,000, A naught, the initial amount, is 3,000. Now let's think about this a second. This bank is telling us that we can double our money if we put it in there in 12 years. Okay? We want to know how much money we're going to have if we put $3,000 in there in 5 years. So we're not going to wait the whole 12 years. If we waited the whole 12 years, we should have $6,000 because our money is going to double. But we're not going to wait 12 years. We want to know how much we're going to have after 5 years. Maybe we need to pull that money out at 5 years. Okay? So anytime you see double or triple or anything like that, or half-life or anything like that, that's going to be B. And the amount of time you have to multiply A naught times B is going to be K. So if it's going to double in 12 years, then K would be 12. If the half-life is 2 days, then half is going to be B and 2 is going to be K. Okay? So I have this problem. So what I'm looking for is A of 5. A of 5 is equal to A naught is going to be 3,000 times B, which is 2. You need to put that in parentheses. To the power of T over K. So that's going to be 5 over 12. And I'm going to go ahead and click off the screen so I can bring up my calculator so I can show you how to put this in, make sure we're knowing how it's put in the calculator. Remember, this is just function notation, so after I plug this in, I'm not concerned with this A of 5 anymore. I'm just concerned with what this is going to simplify to here. So I have 3,000 times 2, and I'm just putting it in just like I had it, to the power of, parentheses because it's a fraction, t over k. So it's going to be 5 over 12. So in 5 years, I'm going to have $4,004.52. Continuing on, let's look at number 2. Final example. A radioactive isotope has a half-life of 5 days. Here we go. Here's these key words. Half-life. Remember when you see something like that? That means B is half. Has a half-life of 5 days. That means K is 5. This means that half-life of the substance decays in 5 days. If 5.6 kilograms are present now, that's A naught. A naught is 5.6. How much will be present after 21 days? So T is going to be 21. Write my formula down. Now, I know some of you are thinking, I'm not going to write this formula down every time. I will highly recommend it. When I work a problem out a specific way, whether I'm factoring, whether I'm solving a problem like today, you should always do it the way I'm showing you. I'm trying to model to you the best way to work the problem so that you can keep up with all your data and show all your work. So we have A of T is equal to A naught times B to the power of T over K. Now I can simply plug it in. So I'm looking for A of 21 is equal to A naught is 5.6 times B, which is half, to the power of T over K, which is going to be 21 over 5. And when I plug this in my calculator and round to the nearest thousandth place, or 3 decimals, I get 0.305 kilograms. And that is how you work problems from note cards 48 and 49, exponential growth and decay.